The research introduces the TTJac Score, a novel evaluation metric for assessing the quality of individual synthesized images in a data-free manner. This metric directly evaluates the generated sample density by utilizing the trained generator's Jacobian, which is approximated using feature extractors and tensor train decomposition to reduce computational costs. The TTJac score is demonstrated to improve the fidelity-variability trade-off when applying the truncation trick. Experimental results on StyleGAN 2 and StyleGAN 2 ADA models across various datasets are presented, showcasing the effectiveness of the proposed metric. This research introduces a novel method for evaluating the quality of images generated by generative adversarial networks, GANs. The generator network, a primary component of GAN models, produces an image from a given latent code. Traditional evaluation methods include using realism scores or the truncation trick, which have limitations such as requiring access to a dataset or assessing fidelity based on input vector norms. The proposed approach defines a metric function that evaluates image quality based on the density of the generator output, utilizing the generalized change of variable formula to compute the Jacobian matrix of the generator network. However, this method is computationally inefficient for high-resolution images due to the need to compute the Jacobian matrix, which poses significant time and memory consumption challenges. To address these issues, the authors suggest employing feature extraction, where the score function is determined by the density of features extracted from generated images. This process involves using a feature extraction network, such as VGG19 or Dino, to extract meaningful features from images. The research pipeline consists of generating latent code samples, passing them through the generator network, extracting features with the VGG feature extractor, computing feature density using the generalized change of variable formula, and approximating metric score samples via the tensor train algorithm. The authors considered two feature extraction networks, VGG19 and Dino, both highly efficient in classification tasks and widely used for extracting information from image data. This research evaluates image features extracted from different networks, comparing the performance of VGG19 and Dino features in terms of time consumption and qualitative results. A StyleGAN 2 ADA model trained on the FFHQ dataset generates 100 images for analysis. The results show that VGG19-based feature density produces comparable outcomes to pixel-based and Dino-based densities, but with significantly less time per sample, making it the preferred choice for further experiments. To accelerate inference time, a two-stage solution is proposed. First, scores are computed for a large number of samples, and then the logarithm density is approximated using these samples. This involves finding the closest point to the latent code in the discrete latent space, computing the score value at this point using the stored density tensor, and utilizing a non-uniform grid for discretization to ensure a uniform distribution of samples along each grid index. Quantitative evaluation of the TT approximation of the TTJac score on a discrete grid for different domains, including FFHQ, AFHQ-Wild, LSUN-Car, and LSUN-Horse, reveals promising results, as presented in Table 2. The proposed method demonstrates efficacy in reducing computation time while maintaining accuracy, as shown through these experiments and comparisons. In generative adversarial networks, GANs, a novel metric function is proposed to evaluate the quality of generated samples. This metric function leverages the tensor train decomposition, enabling efficient approximation and storage of complex dependencies between components. This decomposition facilitates fast inference capabilities, overcoming the limitations of standard iterative methods, which are prone to overfitting and fail to capture underlying dependencies. Explicit methods, such as ANOVA decomposition, are better suited for computing samples, as demonstrated by Chertkov, Ruzhikov, and Oseledets, 2023. The truncation trick, initially proposed by Brock, Donahue, and Simonyan, 2019, balances variability and fidelity in generated samples by evaluating the norm of generated samples and resampling those with a norm exceeding a specified threshold. This threshold determines the balance between variability and fidelity, effectively reducing the number of outliers by removing samples with high norms. Figure 3 presents a qualitative comparison of metrics for individual image evaluation, showcasing the TTJac score, realism score, rarity score, and truncation trick. For each metric, 8 images are presented with the lowest, middle, and highest score values. The TTJac and realism scores are arranged in increasing order from low to high scores, while the rarity score and truncation trick are intentionally reversed for ease of comparison between the metrics. Evaluating individual sample quality in image generation models is crucial for assessing their performance. This study focuses on 4 key metrics: TTJac score, realism score, rarity score, and truncation. Experiments were conducted on various datasets, including FFHQ, AFHQ-Wild, LSUN-Cars, and LSUN-Horse, using StyleGAN 2 and StyleGAN 2 ADA models. A grid size of 32 was employed for discretization, and ANOVA decomposition of order 1 was applied to approximate the metric, which was then converted to the tensor train format. The results reveal a strong correlation between the TTJac score and other metrics, particularly the realism score. Notably, the TTJac score can effectively filter out low-quality images with comparable efficiency to the realism score, without requiring a dataset of real images. This has significant implications for enhancing the performance of the truncation trick, which allows for manipulating image quality at the expense of variability. The authors compare the trade-off provided by the standard criteria based on latent code norm and the proposed TTJac score, aiming to achieve a more desirable balance between fidelity and variability in generated images. The TTJac score offers a promising alternative for evaluating individual sample quality, enabling a more nuanced understanding of image generation models and their potential applications. The authors present a quantitative comparison of the fidelity-variability trade-off computed using the TTJac score and the truncation trick across 4 domains: FFHQ, AFHQ-Wild, LSUN-Car, and LSUN-Horse. For each domain, 50,000 samples were generated to calculate precision and recall, with results averaged over 3 random seeds. Precision recall curves for each domain demonstrate the effectiveness of the TTJac score in achieving a better balance between precision and recall compared to the standard truncation trick. Specifically, the TTJac score curve consistently lies above the truncation trick curve for the FFHQ, LSUN-Horse, and LSUN-Car domains, indicating improved precision with minimal loss in recall. However, the benefit of the TTJac score is not significant for the AFHQ-Wild domain, where the GAN model already exhibits high precision. Additionally, the evaluation of TT approximation accuracy presents the least favorable outcome compared to other domains. Notably, the TTJac score curve for the FFHQ domain initially improves precision by 5% but then declines and falls below the truncation trick curve, which can be attributed to an error in the metric approximation. In contrast, the TTJac score proves highly effective for the LSUN-Car domain, providing a significant improvement in precision with negligible loss in recall. It is important to acknowledge that due to errors in the approximation of the metric score, it is not possible to achieve maximum precision with minimal recall value, as seen in standard precision recall curves. Nonetheless, this comparison highlights the potential of the TTJac score in achieving a better trade-off between precision and recall. The TTJac score is a qualitative evaluation metric that efficiently detects visual artifacts and identifies unrealistic elements across various domains. Figure 6 showcases the results, where 30,000 samples from each domain were sorted based on their TTJac scores, selecting 3 images representing the lowest, middle, and highest score values. The metric assigns low scores to images lacking faces or having unrealistic prints in the FFHQ domain, and those with poor backgrounds. Similarly, in the LSUN-Car domain, it identifies images missing key elements of a car as lower quality. The TTJac score demonstrates high efficiency in evaluating sample fidelity while sacrificing some variability, effectively detecting visual artifacts and identifying unrealistic elements. Comparisons with other metrics show a better balance between fidelity and variability, particularly in the LSUN-Car domain, where precision is significantly improved with minimal loss in recall. Evaluating the performance of generative adversarial networks, GANs, and their variants is a crucial task in image generation. To address this, a novel metric, the rarity score, is introduced to assess the uncommonness of synthesized images. This metric is essential for understanding the ability of GANs to generate diverse and novel images, a key challenge in this field. Understanding the latent space of GANs is also vital, as it provides insights into how these models learn to represent and generate images. Techniques such as feature statistics mixing regularization, unsupervised discovery of interpretable directions in the GAN latent space, and semantic face editing can improve the interpretability and performance of GANs. Moreover, the paper explores the application of tensor train decomposition for solving nonlinear filtering problems, highlighting its potential in industrial trajectory applications. This underscores the interdisciplinary nature of GAN research, drawing from signal processing, control theory, and machine learning. The rarity score is a crucial tool for evaluating GAN performance, as it quantifies the generation of diverse and novel images. By understanding the latent space and leveraging techniques such as feature statistics mixing regularization, researchers can improve the interpretability and performance of GANs. The paper's discussion of tensor train decomposition and its potential applications further highlights the vast possibilities of GAN research, which continues to benefit from insights from multiple fields. In the 2017 IEEE International Conference on Computer Vision, ICCV, a paper titled Adversarial Networks was presented. This research focuses on the development of a novel deep learning architecture known as generative adversarial networks, GANs. GANs consist of two neural networks, a generator and a discriminator, that compete with each other during training. The generator aims to produce samples indistinguishable from real data, while the discriminator attempts to differentiate between generated and real samples. Through this adversarial process, both networks improve in performance, resulting in high-quality generated images. The authors discuss the challenges associated with training GANs, such as mode collapse and non-convergence, and propose several techniques to address these issues. They also explore various applications of GANs, including image-to-image translation, image generation, and data augmentation. The paper evaluates the performance of GANs using metrics like the Frechet inception distance, FID, and the inception score, IS. It also touches upon the relationship between GANs and other deep learning models, highlighting their unique properties and strengths. Finally, the authors discuss potential future directions for GAN research, including the development of more stable and efficient training algorithms, new applications, and the integration of GANs with other machine learning models. The appendix delves into the tensor train (TT) format, a method for representing high-dimensional tensors as a sequence of low-dimensional cores. The TT format is denoted as T, I1, I_D, approximately equals G1, I1, G2, I2, GD, id, where G1, GD are matrices of size, R, and D is the size of the latent space. To find the cores GK for a tensor represented by random elements, the alternative least squares algorithm, ALS, is employed. The ALS algorithm consists of an alternating best fit for each of the cores GK in the order of k equals 1, D. For each core GK, an independent least squares problem is solved, which can be formulated as a standard linear problem. GK, I, equals argmin GK, I, parallel TK_I. RK circled dot operator LK, vec, GK, I, parallel. The grid type significantly impacts tensor decomposition, and the authors consider a uniform grid with parameters A equals 3, B equals 3, and N equals 64. However, this leads to a limitation on the rank of the decomposition due to the discrepancy in the number of equations between different grid points. To address this issue, the authors propose using a non-uniform grid with intervals such that the integral of the normal density over these intervals is equal. In Appendix B, the computation of tensor train cores raises a question of choosing optimal hyperparameters like rank, method, core initialization, and number of iterations. To find the optimal rank, the authors constructed a matrix C describing the pairwise dependency between two components K1 and K2. The normalized cumulative sum of singular values for matrix C is shown in Figure 7 for random pairs of components. Overall, this appendix provides a detailed explanation of the TT format, the ALS algorithm, and the importance of grid type in tensor decomposition, as well as the need for optimizing hyperparameters in tensor train core computation. In the context of tensor train approximation, the authors introduce a novel approach to estimate the optimal rank of a tensor T. They define the element C, junior, JC, at the intersection of the JRTH row and JCTH column of a matrix C, computed using the TT approximation T approximately equals G1, GD. Mathematically, this is expressed as C, junior, JC, approximately equals EIK, K equals K1, K2, G1, I1, GK1, IK1 equals junior, GK2, IK2 equals JC, GD, id, where G1 is the first TT core. By summing along the second dimension of each core, the authors derive a simplified expression for C, junior, JC, approximately equals GK11 1 GK1, IK1 equals junior, GK21 K1 plus 1 GK2, IK2 equals JC, GDK2 plus 1, where GK11 1, GK21 K1 plus 1, and GDK2 plus 1 represent the product of average cores before, between, and after K1 and K2 components, respectively. The rank of matrix C is shown to be equal to the rank of the product of these average cores, which is bounded by the smallest dimension size R of the tensors in the product. This enables the estimation of the optimal rank by evaluating the rank of matrix C computed for the target tensor T. Empirical evidence supports this claim, with Figure 7 presenting normalized singular values for matrix C computed for different random pairs of tensor components. The results demonstrate that the tensor can be accurately compressed with a small rank, validating the effectiveness of the proposed approach.